Hello, very welcome back to our channel. This time we have on the screen a circuit diagram and we have a problem statement and we want to answer it. So it's an objective type question. So let's solve it. So how we can read the problem for the BJT in the amplifier. So it is an amplifier circuit using the BJT. This is your BJT. VBE, that is the base emitter voltage of this BJT, is 0.7 volt. KT over Q, this is called as thermal voltage, and at room temperature its value is about 26 millivolt. Assume that the BJT's output resistance, so output resistance in a small signal model for a BJT is indicated by RO, and you are set that assume it to be very high, and also assume that the base current is negligible. So the current that flows into the base pin of the transistor is also asked to be considered to be negligible. The capacitors are also assumed to be short circuit at signal frequency. So when you have applied a sinusoidal AC signal, you have got these capacitor C1 and the capacitor CE, they will act as a short at the signal frequency of interest. F is the frequency of a signal. So we know that this is output coupling capacitor that couples the output to the load. We know that this is the bypass capacitor that bypasses the emitter resistance RE at high frequency so that gain can be enhanced. Now the input VI is direct coupled. We don't have any coupling capacitor here, so that's why we say it is directly coupled. The question here is the low frequency gain, that is the ratio of VO over VI. Here is your output, here is your input. So we have to calculate or determine the low frequency gain of this amplifier. So VCC is the positive DC power supply, that is 10 volt. VEE, that is the negative power supply, that is minus 10 volts. So we have got dual power supply. Low resistance RC is connected from collector to the DC power supply, and there is this emitter resistance. We know from our previous discussion, it is also called as degeneration resistance. It is there to reduce the gain by some amount, but the advantage of having RE in this circuit is that it provides the stability of the operating point against variations it provides the stability of the operating point to the circuit, because operating point can vary over temperature, noise, disturbance, etc. So having RE makes sure the operating point remains stable. RL is the load resistance and VI is the input, VO is the output. So let us solve this. How we can solve this? So we basically want VO over VI. That's the magnitude of the signal. So there are four options: A, B, C, and the D. Four values are given. So which is, of course, if we don't take the magnitude, the output would be negative of the input because it's an inverting amplifier. Okay. Now, if you do the DC analysis of this circuit, we can actually look at the input side of the circuit first. So input side of the circuit is this side, okay? And the output side of the circuit is this side, right? So we want to find the answer using some quick analysis method. So what we can do, we basically can apply the Kirchhoff's voltage law into this input loop. So let me write here. So we basically can say that this is your VBE, which is given to be 0.7 volt. VBE is equal to 0.7 volt. So what you can do in this loop, I have applied the KVL to get the value of IE, which is the current flowing through this resistor RE. So for that, you see here, this is my VBE. This is the resistance RE, and this is the 10 volt of this VEE. So you see the polarities of the voltages VBE, and I see the current flow direction like this. So the drops in this loop, the voltage drops in this loop will be VBE plus IERE minus 10 equal to 0. So from that, I would say IE would be 10 minus VBE divided by RE. Okay, so here, coming right over here, so we see IE, that would be 10 minus 0.7, because VBE is 0.7, RE is 20 kilo ohm. So it is like 9.3 volt divided by 20 kilo ohm. That comes out to be, we have to see how much is the value. So after calculation, that value comes out to be about 0.465 milliampere. So let me write here 0.465 milliampere. So we have got IE. Now base current is assumed to be negligible. So we say that IC is approximately equal to IE is equal to then 0.465 milliampere. Now why we need a value of IC? Because we have to draw the small signal model of this circuit, because we are asked to calculate the low frequency gain of this amplifier. So the small signal model will be drawn like this. This is your base pin, which is connected to the ground. Here is your collector pin, and then from the collector you have got this dependent current source, which is representing the collector current IC, which is equal to GM times VBE, where VBE is this voltage. Where is your emitter now? Here is your emitter. This is emitter is connected to the ground, because now you have shorted this capacitor right over here. Okay, so for the DC analysis, you have taken into account the RE. Okay, and the collector for the biasing condition, you have taken into account the RE, and you calculated the value of IE, and then you got the value of IC also. Now for the low frequency calculation, that is the low frequency gain calculation, we are deriving the small signal model where emitter is grounded, and then you have this current flowing from collector to the emitter pin. Now you have this resistor RC, because the for the AC small signal AC analysis, these DC voltages are shorted to ground. So VCC is connected to the ground. And of course, this voltage source will also be connected to the ground. Okay. So effectively RE is also connected to the ground. So then you say now this is RC, which is, well, it is connected to the ground. And then you have this RL, which is also from collector to the ground. Okay. So now if you see the output voltage here, which is basically this current source, that is negative of IC times RC in parallel with RL. So it would be like this, and IC is your negative GM times VBE, RC in parallel with RL, and VBE is nothing but your input voltage connected between base and the ground, this input voltage. Okay, so you say that VO equal to minus GM times VI, RC in parallel with RL, and then VO over VI, which is what you are asked to calculate, GM times RC in parallel with RL. Okay, now how to get the value of GM? So GM is basically IC over KT by Q, which is your thermal voltage, right? So KT by Q. Let me confirm it. 1 second. Yeah, or it can also be written as IC divided by VT. So VT is your thermal voltage, which is KT by Q. So IC, you have got it to be 0.465 milliampere divided by 26 millivolts. So 26 millivolts right here. Okay. So that is calculated to be, you can just get cancelled these two terms, 0.46. Here you can write 0.465 divided by 26. Okay. And we can then, this is the value of GM. So once you know the value of GM, you can plug in that value into this expression of output divided by input. Okay, so how we do that? Let us do that. Okay, so here we are. So we plug the value of GM back into this equation. So we would say VO divided by VI is equal to, minus sign is there, and it will be 0.465 divided by 26. This is your GM, multiplied by, what is the value of RC and RL? 10K each. They are in parallel. So right here from the model. So obviously their value is effectively 5 kilo ohm. Okay, and if you solve this, let me check how much this comes out to be. So that comes out to be minus 89.42. So your small signal low frequency voltage gain of this amplifier is option D, which is minus 89.42. Okay, so if you see that we are correct, and we have done the analysis properly, we just have some comments into the comment section. Okay, so till then, wish you happy learning.